Okay, I guess we're about ready to get started. And this week, I wanted to introduce our speaker. This is Channon Visscher. And he is a postdoc at the Lunar Planetary Institute, which is right around the corner. And he's also, he's working in atmospheric chemistry, and so it's atmospheric physics, which obviously it applies into physics, but there's also a lot of environmental work. And you got your degree in Earth and Planetary Sciences from Washington University in St. Louis. So with that, I'll turn it over to our speaker.
Thanks for inviting me. And yeah, it's nice and close. I was just telling him I've actually cut through the woods here once to get to the library. I don't know if I'll do it again anytime real soon, because I almost got lost on the way back. But thanks for inviting me out. And I'm going to be talking about some of the research that I've been working on for about really the last 5 years or so, especially. My undergraduate background is in chemistry, so I would consider myself a chemist after a planetary scientist. And basically what I've been doing is using the methods and techniques of physical chemistry and applying them to problems in the planetary sciences. And it's, I think, been pretty fruitful. And so tonight I'm going to start by giving sort of a broad brush overview of what I mean by substellar objects. I kept that intentionally vague because then I can cast a wide net on what I want to study. Overview of some recent discoveries. What can these things tell us about current formation theories, the evolution of planetary systems? And then I'll get into a little bit more of the meat of the talk, talking about some of the research we've been doing on clouds and chemistry and substellar atmospheres. The role of thermochemistry. When I say thermochemistry throughout the talk, I mean thermodynamic equilibrium chemistry. And then disequilibrium processes, which are dynamical or photochemical. And then a couple applications will be Jupiter's bulk water inventory. I'll try to convince you that that's important, that we know what that is. And then discussion of chemical regimes on brown dwarfs and exoplanets. So although this talk is about chemistry, as far as I know, there's only one chemical equation in the whole talk. And I know this is a physics group, and I work with somebody who is a physicist, so we're constantly arguing about units and appropriate, I want to use R, she wants to use Boltzmann's constant. I want to use moles, she thinks that's ridiculous. So I understand some of the issues there. So, but I just want to give an overview of the basic physics and chemistry, and I hope I can convince you that understanding the underlying physics and chemistry of these atmospheres is essential for understanding the astronomical observations of these objects. When we look at Jupiter, we're looking at a manifestation of the chemistry in its atmosphere, and I think it's important that we understand what's going on beneath the clouds, as it were. So how do we know what we know? When I talk to people and tell them I'm a planetary scientist, I think they have this idea in their head that I'm sitting up in an observatory looking through the telescope, watching Jupiter all night, when in fact I'm in front of my computer every day, like most of you, I'm guessing. But we do use the telescopic observations for our constraints as inputs to our models. Mostly here, Hubble and Spitzer, which is the infrared telescope and space telescope. And now Kepler is in orbit looking for transiting exoplanets. So that'll also be important. We also do rely on a lot of spacecraft exploration, notably Voyager, Galileo, and Cassini, because our topic of study is the giant planets. So we focus on those outer solar system missions. And this sounds simplistic, but we're assuming that the same physical principles apply throughout the universe. And I know that's a very simplistic statement, but it's very important for a modeler, because that lets us develop models that we can trust will accurately explain what's going on. So we don't have to rely on a very simple model like this. Instead, we can try to figure out what physics, which chemistry is operating, such as in the interior of the Earth or in the interior of Jupiter. And as an example of this, you all recognize this as Jupiter's Great Red Spot. But you probably notice this little box up in the corner. That's Hurricane Ike for scale. And my point here is the same physics that's describing motion in that object is describing motion in this object as well. So the same principles are applying, it's just obviously the scales are different. And there are other differences too, cold core versus warm core, so on and so forth. But I hope that makes the point, and also gives you an idea of the planetary scale. Oh, and please, before I go further, if you have any questions, feel free to interrupt me. So the slide's there on screen when you have a question.
Figure, was that old, or what was that?
What's that?
You were comparing height with the other thing on the
This is the Great Red Spot on Jupiter.
Oh, I'm sorry.
Yeah. So it's, you know, they're both, well actually this is cyclonic, that's anticyclonic, but both planetary scale storm systems. So the field of study here, and I want to define what I mean by substellar objects. A substellar object is anything that's not a star. Again, a tautology, but it's important for our purposes. Stars, of course, are anything that have sustained hydrogen fusion, and the classic spectral classes will be a fine girl, kiss me. And this is anything heavier than about 75 Jupiter masses. So that's our stars, our stellar objects. The substellar objects are anything that cannot sustain hydrogen fusion for any length of time in their interiors. And that includes the brown dwarfs, which might have temporary deuterium fusion because they're massive enough for some fusion, which are the spectral classes L and T. And I believe this is, of course, the HR diagram, and it shows the L and T spectral classes there on the end.
What's the 750?
750 is the number of brown dwarfs known as of today. There's 450 known planets if we include all the exoplanets known as of this morning. And there's a mass difference here. Brown dwarfs, anything between 13 to 75 times the mass of Jupiter. If you get less than that, you can't get any fusion at all in the interior, and that's what I'm defining as a planet. So technically, this definition would include Earth, but for the purposes of this talk, I'll be focusing on gas-rich objects such as Jupiter and Saturn, Uranus and Neptune. And this little dot here down in the far corner is a rough calculation I did for the magnitude, or for the luminosity of Jupiter, where it would plot on an HR diagram. So you can plot Jupiter on an HR diagram, and as we're seeing, we're starting to rapidly fill in this gap between the end of the main sequence and the onset of planets. So we're sort of discovering this new frontier of objects that before the mid-90s really were sort of theoretical curiosity. This is one of the great things about this field is we get lots of artistic renditions because we don't have too many images of these things. But here's some substellar objects for comparison. We have the Sun, of course, 5800 Kelvin photosphere, very large, very hot. We have an M dwarf star, which is still hot but substantially cooler than the Sun, an L brown dwarf and a T brown dwarf, and then Jupiter there with its effective temperature shown for comparison. Now, interestingly, you'll notice that Jupiter is roughly the same, if not larger, than the brown dwarfs and even the low-mass dwarf stars. And this is because these are so much more massive; they have that much more gravity, so their radius is very small compared to Jupiter. On the Sun, of course, we have it's that much more massive, and we have radiation pressure, very hot. But for a chemist, these are much more interesting than this because they're cool enough that you can get the formation of molecules, you can get the formation of clouds, you get reaction chemistry happening. So things are happening. It makes for a very interesting study. And like I said, we're starting to discover this in-between region at a very fast pace. And here's a timeline of discovered worlds or discovered planets from prehistory. I put Earth in parentheses because it's really not even entirely clear if we really understood the Earth as a planet until Copernicus or Galileo. But obviously people were aware of its existence in prehistory. 1400 BC, Mercury, Uranus. Of course, Ceres is the largest asteroid between Mars and Jupiter, it's now considered a dwarf planet, I suppose. Neptune. And then Pluto, which is the first and the largest Kuiper Belt object, and also now considered a dwarf planet. And you'll see there's sort of a gap between Pluto and then 1992 we have this weird PSR designation. Depending on how you define the first discovery, because sometimes these things are discovered by going back to data and reanalyzing. This is the first extrasolar planet discovery, but it's orbiting a pulsar, which is not exactly friendly for life. So people were very interested in it, but it wasn't as exciting as it could have been until 95, 51 Pegasi b was the first extrasolar planet discovered around a solar-type star. So this got people really excited because this is a G-type star with a planet around it. The same year, Gliese 229b was discovered, and this is the first bona fide methane brown dwarf. I say bona fide because some of these brown dwarfs are sort of on the edge between brown dwarf and star. But this one definitely is a brown dwarf because it has methane in its atmosphere, and methane means cooler temperatures, as I'll discuss later on. 97, you start seeing more multi-planet systems. 1999, the first transiting exoplanet. As we'll see, this transiting planets are very important for studies of exoplanets. By 2000, there's 50 known. 2003, if you want to blame anybody for killing Pluto, it's this thing, because it's larger than Pluto, and that was discovered in the outer solar system. 2004, we have our first direct image of a planet outside of the solar system, imaged in infrared. By 2005, 180 known. You can see where this is going. It's almost exponential. 2007, we're starting to get to smaller planets with a more interesting location than the habitable zone. 2008, we have the first directly imaged exoplanet with visible wavelengths. So the first picture of an exoplanet. And as of this morning, 445 confirmed exoplanets. That actually jumped since Friday. I think it was 443 on Friday. So these are continually being discovered, and over 750 brown dwarfs as of this morning.
All these planets are bigger than Earth.
Yes.
I mean, they're looking for one the size of Earth.
Yes, exactly. Right now, there's a very strong bias toward big planets that are very close to their primary star, to their parent star. And what I've plotted here is all of the 400-odd planets normalized to Earth. So this is Earth mass log plot, and this is the orbital distance. And you can see we have a pile up here of planets right on top of their star. And the planets tend to be at least 100 times or so more massive than the Earth. And you can see I've got the solar system planets shown there for comparison. So most of these things are roughly the mass of Jupiter. So we still do have a very strong observational bias because they're easier to see. And of course the goal over time is to move this cloud of data points from up here down to here, where we've got a normal orbit, quote unquote, and a normal mass. And I think it's fine to define Earth as normal if that's what we're interested in studying. The triangles here I'll point out are for transiting exoplanets. So these are planets which pass in front of their star from our perspective. So they're eclipsing their stars from our perspective. So there's special geometry considerations that need, for the statistics of these. And of course, like I said, the goal is to push this number, these values down closer to Earth. And that's really the current objective of a lot of NASA's Extrasolar Planets program. The Planet Quest, Terrestrial Planet Finder. You've probably heard of some of these missions. Here on the right is the Kepler spacecraft. This has started detecting exoplanet transits. So it's looking for dips in the light curves of planets over in a small region of the sky. And it's already discovered like 7 new planets since January. So I think this will be very fruitful. And it has the capability of detecting very low mass planets in the habitable zone. And of course the habitable zone, I haven't defined it. It's basically defined as wherever water is stable in orbit, the orbital distance at which you could have liquid water on the surface of a planet. That might be a planet, or it might even be a satellite orbiting a Jovian-sized planet. Think of Europa at 1 AU. It might potentially be able to sustain life. And that'll depend, the size of this zone and the location will depend on the type of star you have. If you have a very hot O-type star, that zone is going to be pushed well out at very large orbits. If you have a cool star, like an M-dwarf star, that zone will be very close, less than 1 AU toward its star. So some detection methods, and try not to stare at this too long, because I get kind of dizzy if I look at it too long. But radial velocity is by far the most common technique for discovering exoplanets. Over 80% of exoplanets have been discovered by this technique. And basically, it's the gravity of the planet causes a wobble in the star's rotation. As the planet orbits its star, they both orbit around a common center of gravity. So the star wobbles from this motion. And obviously, the bigger the planet is and the closer it is to its star, the more wobble you'll get. So this is one of the reasons why we have such a strong observational bias for big stars that are close to their planets, because they're easier to see. And the wobble looks something like this if you plot up the data. I should point out, if you can do this exercise for Jupiter, if somebody else was looking at our solar system, from some alien world, they would be able to easily detect Jupiter by this method, because Jupiter does create a wobble in our sun's motion. And this is very good at getting at the planetary mass. It doesn't tell you much else about the planet itself, but it gives you can get an orbit, you can get a mass. And for that reason, planets discovered by other techniques are often looked at using this technique so that they can get a mass for the planet as well. Direct imaging, this is much rarer, but it's pretty cool. Here we've got direct imaging in the infrared. A couple of examples, and these things have very strange names. 2M1207b, here on the left, it's a planet orbiting a brown dwarf. The planet's about anywhere between 3 and 10 Jupiter masses, orbiting at about 40 AU, about 40 times the distance between the Earth and the Sun. On the right, we have a multi-planet system. You can see the bright dots there. There's 3 planets shown there. This is a young main sequence star, HR8799, and here's the C planet. This one actually has spectra. Now they've gotten a planetary spectra that they've been able to separate from the starlight. So there's some pretty neat stuff being done with very few pixels and very few photons.
What instrument are they using for direct imaging?
Well, on the left is the ESO, the Southern Observatory down in Chile. I'm not sure. Actually, I think this one's Hubble. If I recall the paper, they're talking about using Hubble filters. So I think it's Hubble. A lot of these too. Of course, this looks like adaptive optics. So the bottom one might be Hubble. This top one's probably Mauna Kea or something. Something that you can do adaptive optics on. And here we've got the first visible light image of an exoplanet. This is Fomalhaut b, 3 Jupiter masses, so it's a big planet. It's orbiting a main sequence A-type star at 115 AU, so it's a long ways out. But if you look closely there, you can see they've got a couple little bright pixels there in that box, and they can see motion. Over the course of 2 years, this planet moved in its orbit around the star. Now, the reason they looked for this is because there is this debris disk that had a rather sharp inner boundary. So they assumed that there was something there affecting the distribution of the debris disk. So they undertook this imaging campaign to try to pick out this exoplanet. Planetary transits, this is about 16% of exoplanets. Again, the planet crosses the disk of the star from our perspective. So you're somewhat limited in how many of the planets you'll find by this method, but it's very easy to find planets by this method compared to the others. And you get a dip in the light curve. So the star is doing its own thing, then the planet crosses its disk, planet crosses its disk, so on and so forth. So this represents one orbit of the planet, and here's a nice little corresponding phase diagram. And what happens here, you actually get a secondary eclipse, because you have almost a fully illuminated hemisphere of the planet when it's going behind its star, and then when it dips behind the star, you lose that reflection, so you get a little bit of a corresponding dip in the light curve. So this is called secondary eclipse, and this is the transit. This is very important for determining the radius of exoplanets, because it crosses the front of the star. We have a pretty good idea of how many photons come out of the disk of the star, so we can get a pretty good idea of the radius of the planet by this method. And obviously, if we combine that with the radial velocity, we can get at density, and density, of course, is telling us something about composition. So this is a very good method for starting to characterize the properties of the planet itself, not just its orbital parameters. And it also allows for, in some cases, we can get planetary spectra of transiting planets, because the light coming from the star passes through the atmosphere of the transiting planet on its way to Earth. So I don't know how they do this, but they're clever about it, and somehow they are able to separate out the photons that are coming from just the planet, and from the photons that are coming from the star itself. And here again is this H799, and here's HD209458b, which of course is the first transiting exoplanet, a little less massive than Jupiter, orbits very, very close to its parent star, which is similar to the Sun. And it turns out you need to have things like methane and water and CO2 in order to match the spectra. So we're starting to get chemical information of these atmospheres. And for me, this is great, because now we have some data points that we can compare our models against and try to explain why in the world we'd see CO2 and methane at the same time, because one's very oxidized, one's very reduced. Exoplanets are also telling us a lot about formation theories and the formation and evolution of planetary systems. They suggest planetary migration is very important, because in general these objects are too hot and too close to their parent stars for quote-unquote normal planetary formation. And when I say normal there, I mean sort of, canonical, what we think of. If you talk about planetary formation with a planetary scientist, they're thinking of Jupiter most likely, because that's sort of, the planetary formation. So there's some evidence that some of these things may have formed further out from their stars and migrated inward. And as they did so, they may have been stripped of their atmospheres, and you're left with a much more dense core. That's been inferred for this beast here, Corot 7b. And there is evidence for atmospheric loss from HD209458b. They measure hydrogen in the orbit, for example, I believe. So this is causing us to revisit some of our ideas about migration in the solar system. And these ideas are not new, and they're not mine either. I'm not a disk dynamicist. But this has been a pretty popular topic later. This is called the Nice model. How many people have here heard the Nice model? I'm just curious. I'd say the last 4 conferences I've been to over the past year, I've seen this movie. So this has been sort of a hot topic lately in planetary science. The basic idea is that you have resonances between the orbits of Jupiter and Saturn and the other giant planets. And over time, these resonances can lead to disturbances and eventually to significant migration of the giant planets. And the net effect is that Jupiter moves in a little bit, Neptune moves out in its orbit quite a bit, and these models predict that you get this sort of cataclysmic scattering of objects that are beyond the orbit of Neptune. And some people are trying to connect this to the late heavy bombardment of the moon, which occurred roughly 4 billion years ago or so. So this has been sort of a hot topic, and I think a lot of this Again, this is not new, but I think a lot of it has been spurred by the discovery of exoplanets and this idea that planetary systems aren't just static and behaving in their nice orbits at 5 AU. You actually get movement of even giant planets in their stellar systems. And here's some newer results. I think just came out in March. I got this off the Hubble site. Some of these exoplanet discoveries are causing reanalysis of planetary formation theories. And for the solar system and for Jupiter, the two basic theories for planetary formation are the core accretion model and the disk instability model. In the core accretion model, the idea is that you have the formation of a clump of ice and rock, sort of this planetesimal, that starts forming the protoplanetary disk. Eventually that planetesimal gets large enough, massive enough, that it will allow for the gravitational attraction of the surrounding gas. And that's how you build Jupiter. The disk instability model says that you get a clump of gas in the disk, and that it itself will cause collapse of the surrounding nebula, and you'll form Jupiter that way. Some new discoveries of exoplanets are suggesting maybe you have cloud collapse out of molecular cloud. In a sense, this is saying you can get planets that form the same way as a binary star system, that they both collapse or coalesce out of a cloud. And that discovery is this 2MJO44144 7 Jupiter mass companion. It's right here. They didn't filter out the parent there, but you can see the pixels are a little brighter on that lower left side of the plot. The issue here is, based upon stellar evolutionary models of the parent star, this system is too young for core accretion to occur in the amount of time that's available, because core accretion is a relatively slow process. Also, they infer that there's not enough material for disk instability, so they suggest that you had cloud collapse where the planet formed the same way as a star. So I don't know if I'm not able to judge the merits of this in detail, but just to point out to you, this is stuff that's coming out now, and it's really changing some of the ways we look at the formation and evolution of planetary systems. So to sort of summarize here, I'm going to start moving into some of the chemical models we've been doing. Just basic exoplanet properties. The radius and mass suggest that they are gas giant planets, similar to Jupiter. Their composition is roughly solar. And what I mean by that, they're basically hydrogen and helium with a little bit of everything else. Just like the sun, just like the solar system as a whole. It's almost all hydrogen and helium, and then you have just a little bit of everything else that makes life interesting. Their orbital properties suggest a variety of formation histories and a variety of formation and evolution in the planetary systems. But we're interested in asking what's controlling what we see on the planets themselves. And again, this is back to this idea, it's the same chemistry, but it's operating in very extreme environments. And a nice way to describe this HD 209458b planet, for example, is you take Jupiter and you stick it at 0.05 AU. So you put it right on top of its star. What happens? And again, it's the same bulk processes are occurring, but obviously you're going to have a much different planet than you have in our solar system. So I'm going to use Jupiter as sort of a proxy, and I'm going to tell you that once we have sort of this model for Jupiter, we can apply it to other objects as well. So here's Jupiter. Again, it's a roughly solar composition, mostly hydrogen, mostly helium. You'll notice these add to 100% because this isn't big enough for the rounding. 0.3% heavy elements. So it is almost all hydrogen and helium. This is slightly enriched compared to the sun. I'll show a plot later that discusses this in more detail. But on the sun, this would be about 0.1% heavy elements. So it's the sun with a little bit of extra heavy elements. The basic structure here is you have this outer molecular envelope. Then you have this sort of metallic hydrogen metal mantle, if we can use the word mantle. It's a large metal layer. and then a core of ice or a combination of ice and rock. It's very warm. It emits more than twice the radiation as it receives from the sun. Low 1966, I think, was the first to really point this out. And that suggests that the interior is very warm and that the interior is convective. And because it's convective, we infer that this molecular envelope is well mixed, that it's a roughly homogeneous composition. So the effect of that is when we observe Jupiter and we measure a gas in its atmosphere, we assume that this methane abundance, for example, represents the carbon inventory of Jupiter's entire atmosphere, because it's thought to be well mixed because of this hot internal convection. And by the way, I didn't point this out, but this is the other 0.3% of this up here. Mostly methane, some ammonia, some water, but we really don't know how much exactly. That's one of the things we'll be talking about. H2S and then all the others. So chemistry is obviously dominated by these major elements here, C and OS. Okay, here's some chemistry now. So I'm going to spend some time talking about this. Here we have temperature and pressure, and I've got this plotted so that high temperatures and high pressures are down in this corner. So basically you're looking at Jupiter, and as you go deeper in Jupiter's interior, the pressures go up, the temperatures go up. Gliese 229b is a T dwarf, T brown dwarf. Got an example of an L dwarf. Here's this transiting exoplanet. It has a much stranger profile. It's very hot because it's very close to its star, so it receives a lot of stellar radiation. And then finally a low mass dwarf star. So these can all plot together. And this shows the major gas chemistry predicted by chemical equilibrium. And this is just basically chemistry 101. We have a pressure, we have a temperature, we have a composition X. We can calculate what we expect the speciation to do of each element. And I've shown one-to-one lines here. So the way to interpret this is, along this line, methane, carbon monoxide have an equal abundance. To the left of this line, methane dominates. To the right of this line, carbon monoxide dominates. CO is present over here, but it's in much lower abundances. So, same here for nitrogen. You have ammonia dominating on this side, molecular nitrogen dominating on this side. Sulfur does the same. We can do this for a number of gases. But the upshot here is carbon is mostly found as CO on L dwarfs. It might be CO, or it might be methane on T dwarfs. And on things like Jupiter and Saturn, we expect carbon to be present as methane. And this is what we observe. So my point here is to show that thermodynamic equilibrium can tell you what gases you expect based upon the elemental composition of that planet. Clouds are also obviously very important. They strongly affect what we observe, and they do that in two ways. First of all, if you form a cloud, you have to make it out of something, and what you make it out of is something that came from the atmosphere in the gas phase. So every time you form a cloud, you remove something from the gas phase. You might remove an absorber. If you remove an absorber, it'll change the spectra and you'll change the appearance of the planet. You also introduce particulate matter. Obviously, this is very basic. On a cloudy day, the sky looks different than on a clear day. It's because you have droplets or ice particles floating around above you. And that's because of reflection and scattering of the cloud particles. And this just shows the basic physics of this effect, I guess. You have illuminated systems like the Earth and Mars, and Jupiter, and then you have self-luminous systems like brown dwarfs. They give off their own light, so there will be some effect there too of the clouds. The clouds will behave differently on each of these systems. And Jupiter hotspots, which I'll mention a few slides down the road here. Things can get complex pretty fast, and this is cloud chemistry for Jupiter, T dwarfs, L dwarfs, and then getting into the L to M dwarf transition. So this is what equilibrium chemistry predicts for the atmospheres of substellar objects. And this is some weird stuff. This is pretty normal. We have ammonia clouds. And when you look at Jupiter, you're pretty much seeing ammonia clouds. That's what really reflects a lot of the light at the top. You have a water cloud, like on Earth. there's a layer of water clouds. But then you get into weirder stuff. You have, I want to point out in particular here, sodium sulfide clouds. I don't know what that would look like, but thermochemistry predicts that that's what's going to happen. In a warmer object, this cloud is shallower because the object is hotter. The colder something is, the more things you can get to condense, right? So the hotter you get, the less condensates you'll have. And by the time you're getting into a star, only very refractory minerals will condense. So here we have sodium sulfide. It shows up on Jupiter pretty deep, gets shallower and shallower. Eventually, it's too hot for sodium sulfide to condense. The other thing I want to point out, you'll notice here again, you have methane, which dominates the upper atmospheres of Jupiter and Saturn. Also in the upper atmosphere of the T-dwarf. You have CO down deep, but by the time you get over here, CO is now dominating over methane. Other weirdness too, iron metal cloud predicted by equilibrium. Magnesium silicates, that's rock, that's what the Earth is made of, clouds. Now this seems fanciful. I just wrote a paper on dealing with magnesium silicate clouds, and there is some observational spectral evidence for crystalline silicate features in brown dwarfs. So there is some observational evidence that you do have these cloud layers about where we'd expect them in the atmospheres of these objects. But I pointed out methane and sodium to make this point. Here we go from, see we got M here, so we go from a low mass dwarf star to cooler objects. So we go from M through the L dwarfs and then to the T dwarfs. And by the time we get down here, we're getting close to planetary regime. If you look at the sodium line, you can see that that disappears as you go to cooler objects. If you look at the methane line, or the methane absorption here, you can see that that disappears as you go to hotter objects. So the point I want to make here is that the thermochemistry is pretty good at telling you the bulk properties, the bulk chemical properties of these objects. These are spectra, near-infrared spectra of these astronomical objects, and this simple Chemistry 101 thermo calculation is telling you why this feature disappears when you cool off. That's all fine and good, but substellar atmospheres are not in complete equilibrium. It's a good first approximation, but they are not in complete equilibrium, and this is where it gets interesting. You have atmospheric mixing. Because of this convection, the mixing can actually give you departures from equilibrium. You have photochemistry. UV sunlight will drive chemical reactions in the upper atmosphere and push you out of chemical equilibrium. So you have to include these effects in chemical models. Now, the traditional approach has been to treat all these separately. My thesis, for example, was on thermochemistry. So that's pretty much all I did. If I had to worry about one of the others, I would do a separate calculation for mixing or for photochemistry. But a new approach, something we've been working on about the last year and a half over here at the LPI, is combining all three of these processes into one model. So we now have a numerical approach that does this. It does thermochemistry, photochemistry, and mixing simultaneously. And this is based upon the JPL Caltech's kinetics code. We have a database of 100 species, getting close to 1,000 reaction pairs. So basically we let the chemistry go, we let it absorb photons, we let it have atmospheric mixing, and in principle we can apply this species list and this reaction list to any object, as long as we have a pressure temperature profile, as long as we can say something meaningful about the available UV flux and the convective mixing rate in that atmosphere. So I'm going to talk about a couple of applications of this, and this is really the main one we've been working on. This is a problem of Jupiter's water abundance, and what is it and why do we care? It is important, and there are several reasons why. First of all, we expect water vapor to be relatively abundant in Jupiter's atmosphere. Now, when I say relatively abundant, I'm talking about 1,000 ppm or so, which is not that abundant, but again, we're sort of neglecting the fact that it's all hydrogen and helium and we're focusing on these heavy elements. We expect a lot of water because water is the dominant oxygen-bearing gas, and oxygen is the third most abundant element in the solar system. So there should be a lot of water there. If you have a lot of methane, you should have a lot of water. Water plays a large role in weather. Obviously, we have cloud formation. The transfer of energy is through thunderstorms or lightning storms. So water is important in that regard. It's important in the thermal structure of the atmosphere. And finally, it's very important for constraining formation models. One of the key differences between the most popular formation models for Jupiter today is how much water they predict in Jupiter's atmosphere. Some predict very high abundances, some predict very low abundances. So if we can really figure out what the Jovian water abundance is, that'll help us to constrain formation theories for Jupiter. And what I've plotted here, again, I mentioned this enrichment. This is the enrichment of various elements relative to solar. So the sun would plot along this dotted line relative to solar hydrogen. So I basically take carbon on Jupiter divided by carbon on the sun. Again, this is a ratio. There's more carbon on the sun than there is on Jupiter, but the concentration is higher on Jupiter than on the sun. Does that make sense? So this is, again, it's a ratio. So we have this enrichment here, and you can see they're all roughly, that one's a little low, but they're all about 2 to 3 times solar. This is kind of surprising because some of these are much more volatile than others. So how do you get this sort of uniform enrichment in heavy elements? Water is weird. What's going on there? It's lower than solar, and we really don't have a good constraint, a good observational constraint right now on the water abundance. Why is that? Well, first of all, it's hard to measure because of cloud formation. When you look at Jupiter through a telescope, and if you're going to do spectra on it, and say you want to get the water abundance, so you're going to do some infrared spectra and look for absorption features, you will be getting photons from this region in the atmosphere, which is pretty much above the water cloud. Again, I mentioned when you form a cloud, you remove gases from the atmosphere. So here below the cloud, we have quite a bit of water. As soon as you start forming this water cloud, the water abundance in the gas phase drops rapidly. So most of our remote sensing measurements of the water abundance are up here above the cloud, where the water abundance is very low. So we don't have a very good idea of what the water abundance is down below the cloud. So the solution, of course, is let's drop a probe into the atmosphere. And again, this is before my time in the planetary sciences, but the Galileo probe fell into Jupiter's atmosphere in December of '95, and it went down to about the 420 Kelvin, 20 bar level, before it finally failed because it got too hot and the pressure was too high for the electronics. Surprisingly, it measured a rather low water abundance, about half of what people are expecting as a minimum. People are, again, expecting about 1,000 ppm as a minimum, but this measured 400 ppm, plus this abundance was still increasing when it stopped sending back the signal. So people argue about, well, would it have continued to increase? Did we really get to this deep, constant profile of water? What's going on? And the reason is because it entered this unusual hotspot area, and this is a localized region of downwelling material, and this downwelling material is very dry. And in meteorology, the basic concept is anytime you have uplift, you can get cloud formation, condensation. Anytime you have downwelling, you're going to have clear skies, thin cloud layers. It's going to be drier air. And this is basically what people think is happening here, that this is a localized meteorological phenomenon. Now, the word hotspot, I think basically is because it exposes regions of higher temperature. It's much easier to see the hotter interior in a hotspot region because you have thinner clouds, and this shows up pretty readily in infrared images. And this here is an image of what a hotspot region looks like. And when I tell people about this hotspot story, they kind of think, it is a dumb luck that you fell into a hotspot with the Galileo probe, but it's not as if you fell into this tiny little hole in the clouds For comparison, this white square here has the area of Texas. So this is a pretty big region. So it's not, it's not really dumb luck. It's just, that's quite a bit of real estate there. And you can see here the clouds are thinner. So this is the type of region that the Galileo probe fell into. So it's hard to get by remote sensing measurements. It's hard to get from the probe because of this unusual location. So something we've done is using a chemical model to estimate the water abundance. And we do this by looking at how water affects things that we can observe in Jupiter's atmosphere. And here's my one chemical equation in the talk. And basically this says water forms carbon monoxide. The point I want to make here is if you add water, you get more CO. If you take away water, you get less CO. You have this equilibrium relationship. So we want to measure CO in the atmosphere, but according to equilibrium calculations, there shouldn't be any CO in the upper atmosphere. It's all methane. There shouldn't be any CO at all. But we do actually observe about a part per billion carbon monoxide in Jupiter's upper atmosphere. This is way out of equilibrium, like 20 orders of magnitude out of equilibrium. So the idea here is that you have mixing from regions where CO is more abundant up to the upper atmosphere where you can observe it. So we have to consider atmospheric mixing. We're taking a parcel of gas from deep in the atmosphere, and convective transport is bringing this up into the upper atmosphere. The key here is that the mixing is happening faster than the chemical reactions. So in physics, the shortest time scale always wins. So you can do this on a time scale comparison. The time scale of chemistry here compared to the time scale of atmospheric mixing. So if you want to figure out what's going on with CO in the upper atmosphere, you have to consider the rate of mixing, the rate of the relevant chemical reactions, and the water abundance in the first place, because if you have more water, you have more CO. And that's one of the things we've been working on. This is Impress with Icarus. And this summarizes some of our results for CO chemistry in Jupiter's atmosphere. So I'll spend some time here. These gray lines here show the equilibrium profile. So let's focus here on the solid line. If we obey equilibrium, CO will follow that line in Jupiter's atmosphere. This here is the observed. So you can see equilibrium is much different than observed. But what happens here is, as you go to higher altitudes, the temperature also goes down. As the temperature goes down, the rate of the chemical reactions also goes down. That's the basic rule of thumb. Higher temperatures, faster chemistry. Lower temperatures, slower chemistry. Eventually, you'll reach a point at which the time scale for mixing is almost the same as the time scale for the chemistry. And what happens here is that mixing drives the atmosphere out of equilibrium, and you freeze in the CO abundance. And this is called quenched chemistry. And the reason it doesn't change is because above this region, the chemistry is too slow to do anything. You've basically frozen it in. And you can see that we're using this to get at how much water do we need to get the CO abundance to match what we observe with spectroscopic observations. And the answer we find is that, well, it's somewhere between 2 and 4, probably about 2 and 3 times solar. And this is consistent with the other heavy elements, so that doesn't seem like a very big deal. But I'll point out that nobody's ever looked at this transition in this way before. It's usually treated as a pure timescale comparison. And this rules out formation mechanisms which require large amounts of water. So that's the answer for that. How much time do I have here? Just quick comparison. Our results for Jovian water are roughly consistent with other constraints. It's been suggested that they have these moist convective thunderstorms on Jupiter, and they predict, or they infer a cloud-based temperature based upon their observations of these thunderstorm clouds. These cloud-based temperatures are roughly consistent with the water abundances that we get from our CO chemistry constraint. So there are other ways we can sort of get at this problem of how much water there is. And until we have future missions, whether it be the Juno mission with microwave observations or future missions with more probes so that we can drop it into more than one location on Jupiter, we're going to be stuck with the chemical models and these other sort of indirect estimates of the water abundance. So that's Jupiter, and that was sort of my example of what mixing is doing. Now I'm going to close by talking about some substellar photochemistry and getting back to exoplanets. Obviously, if we take Jupiter and we move it in to 0.05 AU, that's going to dramatically increase the amount of UV photons that it experiences in the upper atmosphere. So we expect much more rigorous photochemistry on these objects. We can even get, again, atmospheric evaporation like we see for HD20945B or CRO7b. And you have huge differences between the day side and the night side. Most of these are spin locked, so the same face will be toward the star throughout its orbit. So you can get this very dramatic difference between noon and midnight. This is like 1,000 Kelvin, roughly, difference. So obviously this is going to have a very large effect on the weather of this object. You might have clouds over here. For example, you might have a sodium sulfide cloud here, but there's no way you're going to get any significant cloud formation on the day side. It's just too hot. So an outstanding question is, what are the relative roles of the thermochemistry and photochemistry? How deep do you have to go before thermochemistry takes over? Or is photochemistry just controlling everything, and what are clouds doing? And so this is something that we're just starting to get into with some of the exoplanet modeling. We started with Gliese 229b, and I just want to point out a couple of examples here. We can separate the chemistry into these different regimes. So down deep we have thermochemistry, that is equilibrium, and then above it we have quenched chemistry. And these are eddy diffusion coefficients, so the faster the mixing, the higher the KZZ value. And up here, this is just molecular diffusion where it drops off in the uppermost atmosphere. But you can see we quench pretty deep on this object, and we have this disequilibrium mixing of CO, and it's similar to what's inferred from some observations. I like this example because it shows three chemical regimes. This is ethane on the brown dwarf Gliese 229b. We have thermochemistry down deep. Then we have departures from equilibrium because of mixing. And then we have production from photochemistry in the upper atmosphere. So UV photons are causing chemical production of ethane in the upper atmosphere of this brown dwarf. So looking at exoplanets, again, if we take Jupiter and move it in really close, we have a flux of UV photons, which is like 10,000 times than that for Jupiter. So we're really cranking up the photochemistry. Unfortunately, there's not been a lot of work done in this area. There's a couple simple hydrocarbon models and a more recent sulfur chemistry model. But neither of these really addresses this question: how deep is this crossover between a thermochemical regime and a photochemical regime? In other words, we want to know which chemistry do you need to use to figure out what's responsible for giving you the spectra that you can observe. And there's a crude way of doing this. This is something we did in 2006. The solid line here shows our equilibrium results. The dotted line shows the photochemical results of Danny Liang. And where they cross over is where photochemistry will push the atmosphere out of equilibrium. And this is around the 10 millibar region. And coincidentally, this is where your spectral forming region is. So it's important to know which one of these chemical regimes is dominating in the upper atmospheres of these objects. And now with this new method, we're hoping that we're able to do this instead of this sort of separate crossover effect. We can model all comprehensively. And so here's some very fresh results. This is very preliminary and subject to much further revision. But this is a model for a hot Neptune, GJ436b, 22 Earth masses, very close to its star. But it's around an M dwarf. So compared to the Sun, that lowers the flux a little bit, but 0.03 AU is pretty close. And this blue dashed line shows equilibrium, which really is just reflecting the weirdness of its pressure-temperature profile. The UV flux is so high that we have to kind of do this in a stepwise fashion. So first, we do equilibrium, then we calculate what happens without any photons. That's the green line. We get quenched chemistry, just like on Jupiter, just like on probably about everything else that has carbon chemistry. if we turn photochemistry on, if we let the photons start absorbing, or let the species start absorbing photons, we start getting photochemical production of CO. So all three processes, thermochemistry, mixing, and photochemistry, is going to be important in the chemistry of this hot exoplanet. So to summarize, basically the chemical behavior of any given object depends on the structure, that is the pressure temperature profile, what your basic composition is, the atmospheric dynamics, how fast is the mixing in the atmosphere, for example, and the available UV flux. That's going to govern what chemical regime you're in. I hope I've demonstrated that cloud formation and disequilibrium will have a very strong influence on the appearance of these objects, especially spectrally, and that exoplanet discoveries are really driving planetary research. How do the planets evolve? What's their bulk composition? How do the systems form and evolve? How do planets form in general? And what atmospheric processes are influencing what we can observe? And so I hope, like I said, we're getting into the exoplanets, and I do think this will be exciting because we'll be able to characterize exoplanet atmospheres, and hopefully we can get to the point where we can explain what the astronomers are seeing through their telescopes by telling them what physics and chemistry are doing it for them. So with that, I'll close, and I'd be happy to take any questions you might have. Thanks.
Questions?
Let me quick show you my cartoon. This is equilibrium, and I'll show you what happens if we turn mixing on.
Ooh.
And it reaches a steady state. So that's you're quenching here and you're mixing it up to the upper atmosphere. So. Basically what happens here is down here you have thermochemistry dominating, and you can see all my models are converging on this equilibrium. So down here we have equilibrium prevailing. The only reason equilibrium is prevailing anytime is if the chemical reactions are fast enough to give you that equilibrium. There's the classic example is your diamond ring should be graphite because graphite's more stable than diamond. The only reason you're not reaching equilibrium is just because the kinetics aren't there. But here, if you're at these very high temperatures, like in this gas system, kinetics are fast enough that you can get equilibrium between all the species in the atmosphere. You will reach the minimum energy configuration.
Oh, I see. It's similar to metallurgy where you put
Right.
water and it reduces.
Yeah. If you drop it. Yeah, that's where the quench idea comes from. If you drop your slug in water, you've stopped the chemistry because it's too cold. Yeah, and then the mixing will take over and bring it up.
I just had a question about the basic research. How much of it is based on data that you've received, and how much of it on computer simulations?
That's a good question. We try to constrain any. Let's see if I can find a. We try to constrain as much as we can based upon observations. So KZZ, that's a measure of what the mixing rate is. It's the eddy diffusion coefficient. This is inferred from observations. And also from theory. So we try to reach sort of the best guess, based on mixing laws and things like that. Methane we can observe, so we know that the basic picture here we know is correct because we see methane, it's the dominant gas. But all of this in between is model. But we are trying to tie it in with observations. So what we'll typically do is we know the atmospheric profile down to 20 bars from the Galileo probe. But obviously this goes much deeper than 20 bars. We go down to 10,000 bars. Well, obviously we can't get down there to measure that. So we have to do an extrapolation, an adiabatic extension of the atmospheric profile, which is, again, it's a calculation, but that's pretty safe part of it. So we have a PT profile, we have an atmospheric composition based upon measurements, spacecraft measurements and such. And then the chemistry is modeled. And if it works, it's great because you should match these sort of observations. I don't know if that gets at your question, but essentially it's a lot of a numerical simulation. But the key is if we can try to tie that in with observations.
Also, another thing, I noticed on one of your plots you had the, what was it, carbon monoxide gas that was at different layers. It wasn't just at one layer.
Yeah. I think...
like that one showed it.
Yeah, the basic idea is here just that it doesn't mean necessarily... There's CO throughout this whole region. It's not so much that they're separated, but that, all the gas down here is CO instead of... All the carbon, for example, you have much more CO down here than you have up here because it's hotter and deeper, and higher temperatures tend to favor monoxide over mist.
You had one diagram, the HR diagram, where you had the end of the main sequence and the beginning of the planets.
Yes.
What's the reference to that?
I have no idea. Like this point here.
What was the source
of this HR diagram?
Yeah.
Pulled it off the web. Yeah. I did this calculation like about a year ago. It's actually kind of hard to compare, and if any physicists or astronomers here have a good idea of, I've been really wanting to create an HR diagram that has one consistent luminosity scale that I can put anything from O all the way down to Jupiter on. The problem is a lot of that information is hard to get for the brown dwarfs because they're so red. All the magnitude information is given in the red band passes or the infrared. So it's hard to find good one-to-one comparisons. This comes from a textbook somewhere, but I can't, off the top of my head, I can't recall which I got off the web somewhere.
You've used the term brown dwarf several times. What about black dwarfs, or is that a term that astronomers even use?
I've not heard that, but people do speak of carbon planets,
right.
Which I guess you could, that would be an apt term. Brown dwarfs aren't brown, by the way. They're actually purple. Is probably the more likely color. Adam Burrows, Arizona, has done calculations on this and what the light curve and such should look like, and the evolutionary history of brown dwarfs. And he concludes that they're actually really purple. So they're kind of like a smoldering. I guess they're it's kind of brownish, I guess, but I don't know. Very very dim and visible, but IR, they're decently bright in the IR.
Okay, anything else? All right, let's thank our speaker.